Well, hi there, everybody. We've been talking a little bit about circular motion. We just had an introduction to it in our previous episode. And here you can see some pretty cool circular motion. We have what appears to be a corgi running around in a circle on a merry-go-round that's rotating in the opposite direction. That equal and opposite thing. That might be coming back to hit us at some point in the future. But for right now, what you need to know is that let's just pay attention to the corgi because it's cute. That as he moves in a circle, he's moving in a linear direction. And I don't mean by that I don't mean a straight line. I mean he's moving along the surface of the merry-go-round. But at the same time, his angle is changing. Let's say if it's measured from the center toward you, the viewer, then the corgi was at 180 degrees just a moment ago, and now the corgi is at 0 degrees, and it keeps changing. So there's a connection between the angular movement and the movement along the curved path. And that's what we're going to do today, is connect angular movement to linear movement. Okay, again, I don't mean linear in a straight line. I mean the actual movement in meters or in inches along a path. Of course, you'll remember that if angle is measured in radians, we have a simple relationship, and it's this. I'll put it right up here. It's that the arc length is equal to the radius of the circle times the angle. Again, if the angle is measured in radians. Well, what if things are moving? Well, then you're going to get a change in arc length. That is a change in position. And you're also going to get a change in the angle. And so, assuming that the circle stays the same, we have that delta S, okay, the change in arc length, is equal to the radius times the change in the angle. If we look at a circle, the center's maybe about here, okay, and let's have 0 be out in this direction. As this moves around in this direction, then a point on the circle, let me switch colors here, then a point on the circle will also move in this circular path. Okay, right there would reflect an angle about this big, and as it keeps moving and keeps changing its angular position, okay, it also changes its physical position with regard to its starting point. Okay, now these things happen at the same, what's the word I'm looking for? Time. They happen at the same time. And so the change in arc length and the change in angle are occurring simultaneously. Therefore, we can divide both sides by that time, and we'll in fact be dividing both sides by the same number. But I want you to notice what we have here. On the left side over here, we have something that would be measured in meters or inches or some unit of length, distance. And we have down here a unit of time. So let's say it's meters per second. That's a speed. But over here, let's factor out the r. We would have delta theta over t. That's the change in angle divided by time, which we just learned recently is called the angular velocity or the angular speed. And we use the letter omega to represent that. So this simple equation turns into the relationship that velocity is the radius times the angular velocity. Now let's do a quick little unit check on this guy. Let's suppose we have the velocity here measured in meters per second. Okay? And let's suppose that the radius is measured in meters, as it would have to be. What does that leave for omega? Well, it would mean that the angular velocity would have to be measured in inverse seconds, right? But we learned that a radian is sort of the unitless unit. So if this is in radians per second, then all of this works out perfectly. If it's in degrees per second, this equation isn't true. Okay, but in radians per second, it's perfect. That's one of the reasons that we use radians, is because it just simplifies out of so many things. Similarly, if we looked at the change in velocity divided by time, that would be r times the change in omega divided by time. And so we would get that the acceleration, that's what change in velocity divided by time is r times the angular acceleration alpha. And a unit check would be meters per second squared equals meters times radians per second squared, and the radians vanish. Now, what do I mean by that little t right there? Well, that has to do with what's called tangential acceleration. By tangential acceleration, what I mean is acceleration, let's say an object's here and it's speeding up as it moves around the circle. Its tangential acceleration is the acceleration that's tangent to the circle. So at that point, it's accelerating that way. At this point, it would be accelerating this way. At this point, it would be accelerating this way. Well, not quite. That wasn't quite a tangent. They're more like that. So we have tangential acceleration that causes the object to speed up or slow down as it moves along the circle. So if it's moving this way, for example, and the acceleration is in the same direction, then it speeds up. If the acceleration is in the opposite direction, it slows down. What about an acceleration, let's say at this point, that's inward toward the center of the circle or outward away from the center of the circle? First, I want you to notice that those are perpendicular to the tangential acceleration. And second, I want you to notice that both of those are in the same direction that a radius from the center of the circle would be pointed. And so those would be called radial acceleration. The total acceleration is the vector sum of the tangential acceleration plus the radial acceleration. And don't forget those are in fact vectors. In fact, the things we're talking about here are generally vectors. Even the angular acceleration and angular velocity, those count as vectors too, although we haven't discussed what direction they would be in. So let's try a little problem here. A wheel on a car has an angular acceleration of 8.5 radians per second squared. If the wheel has a radius of 13 inches, what is the linear acceleration of the car in feet per second squared? That's our first question. And then how many rotations did the wheel make in 10 seconds? Let's take a look at all of that. How do we begin? As per usual, we list variables. Notice that I wrote that the angular acceleration is just 8.5 inverse seconds squared, which is fine because a radian isn't really a unit. The initial angular speed is 0. I could also add in there, if we wanted to do it in a different way, that the initial speed is 0, right? The radius is 13 inches. We want our answer to be in feet per second squared. We can either make that change at the end or we can make it right now. And I'm going to choose to make it right now. So why don't we call that 13/12 feet. Okay? And you can divide that out on a calculator. And the calculator says that that's 1.083 feet. Okay? So how many, what is the linear acceleration of the car? Now in this case, I'm not talking about the angular acceleration. We already know that. Well, the linear acceleration, A, is just r times alpha. And so it's going to be 1.083 times alpha, which is 8.5. Please pay attention to units. This is feet. This is inverse seconds squared. So when we do the multiplication, we get 9.21. Let's round that to 9.2 feet per second squared. Now, what does that actually mean? Well, what it means is if we have an object that's moving in a circle, okay, there's the center, and we can start it from any place. We'll start it here, and it starts speeding up faster and faster and faster as it moves in that circle, okay? The angle that it passes through is increasing faster and faster and faster, okay? That's alpha, the angular acceleration. And its actual movement, its speed, if it had a little speedometer on it, is also increasing at a rate of 9.2 feet per second squared. So that's how we do that. So now that we've answered that, we have to answer how many rotations did the wheel make in 10 seconds. And there's another piece of information here that I haven't listed in my variables, and I probably should. We haven't used it yet, but the time is 10 seconds. Let's assume that that's to the nearest second, so I'll put a decimal point there. Why are we finding theta or delta theta? Well, you see, a rotation is a measure of angle. Just like a degree is a measure of angle, there are 360 degrees in a circle, and a radian is a measure of angle. There are 2 pi radians in a circle. How many rotations do you think it takes an object to make one complete circle? That's right. One rotation is one complete cycle or one complete circle. And so we have some various connections here. So how do we use these variables to come up with delta theta? Well, we have a formula, and it is that angular displacement is initial angular velocity times time plus 1/2 acceleration times time squared. Not the only formula we could use, but it's the one we choose to use. And so that's going to be 0 times time, which is 10 seconds, plus 1/2 times 8.5 times 10 squared. Okay, so that gives us an angle of 425 what? Oh, well, this was in radians per second squared, that angular acceleration, and this is in seconds squared. So this is going to be in radians. Now, I told you it's not a unit, but I'm going to write it anyway just for clarity, because you see the question asked for the answer to be in rotations. How many rotations did it make? But this is pretty easy to understand if we use a conversion factor here. It turns out that one rotation, one cycle, is equal to 2 pi radians. So if we do a little canceling here, radians cancel, we'll have an answer that's in rotations. 67 rotations. Actually, I made a mistake. I made a rounding error. My calculator actually says 68 rotations. Glad I caught that. I don't want to confuse anybody here. Okay. And so that's the connection between linear motion and angular motion as an object moves along a circular path. Next time, we're going to talk about what happens if the acceleration is not along the path, but is toward the center. It's really cool. Come back next time. Bye-bye.